Welcome to homework.
So in this problem, write the molecular orbital electron configuration and determine the bond order and number of unpaired electrons for the following. For the first one, we have C2 plus, so we need to calculate the number of valence electrons to fill in the atomic orbitals. So we see that the configuration for carbon is going to be 2s2, 2p2. And we know that there's a charge of positive 1, so we subtract 1 from the electron count. So each of them will contribute 4, and there's a total of 7 electrons. So in the 2s shell, each of them will contribute 2 electrons. In the 2p shell, one will contribute 2, the other will contribute 1. So let's fill in the bonding first because that's lower in energy. And you see we end up with 1 unpaired electron. So now we need to determine the bonding order. Bonding order is equal to bonding minus antibonding divided by 2. So we can see there are 5 in the bonding, 2 in the antibonding, and divide that by 2. We'll get 3 over 2, or 1.5. We also want to write the molecular orbital electron configuration. So we have sigma 2s bonding. We have 2 in that molecular orbital. We have sigma 2s pi, or 2s anti-bonding, and we have 2 in that orbital. And then we just have the pi 2p bonding. We have 3 in that one. And that's going to be our configuration. So then now on to N2 negative. We see the electron configuration is 2s2, 2p3. Each contributes 5 electrons, and we have to add 1 more, so we have a total of 11. So fill in the electrons in the atomic orbitals. So the 2s is completely filled, and then each of them is going to contribute 3 from the 2p, and there is 1 extra electron, so we're just going to put another one here. So now fill in the bonding molecular orbitals first. There are 2 pi bonding molecular orbitals and antibonding, and we know that we have 7 2p electrons. We do end up with 1 unpaired electron, and that is in the pi antibonding. So now for the bond order. So count the number in the bonding orbitals. We have 8 minus 3 divided by 2, so that's 5 divided by 2. And that gives you 2.5. Now we can write out the electron configuration based off of the molecular orbital diagram. So we have sigma 2s 2, sigma 2s antibonding, and there are 2 in that. Then we have the pi 2p bonding, we have 4 in that, and then we have the sigma 2p bonding, and we have 2, and lastly pi 2p antibonding, and then we have just 1 in that one. Now for the last one. So then for the last one, the electron configuration of beryllium is going to be 2s. So we have both the 1s and 2s to fill in. So we see we have a charge of -1, so we're going to add an extra electron. So 1s is completely filled. And then the 2s, you can see that beryllium has 2 electrons in the 2s. We need that extra electron. So because of that extra electron, we can't put it in the 2s, so we actually have to go to the 2p. So this should actually be higher than the 2s, but I've drawn it here on the side. So it's just going to be filling in the pi 2p bonding. So we can write out the electron configuration. And this is what we would end up with. So now we can determine the bond order. That's number of electrons in bonding orbitals minus the number of anti-bonding electrons divided by 2. So it would be a bond order of 1/2 or 0.5. We see we do have one unpaired electron in this one as well.